Okay, so it's about 6:05, so we can start the official welcome and get everything started. So good evening and welcome, everyone. Thank you for joining us tonight for MIE's Research Spotlight. It's our fall edition of the Research Spotlight. We're really pleased that you could attend our virtual session, and we're looking at in the new year of perhaps moving to in-person, depending on how things go. Tonight's session is virtual. Tonight we are joined by our MIE professor, Greg Jamieson, who took on the role as interim chair of MIE just this past July and will be with us until at least July and potentially longer, hopefully. Greg has been an industrial engineering professor with MIE for a number of years and continues to advance the area of human factors through his undergraduate and graduate teaching and research contributions. Greg is also the first industrial engineering professor to hold the Clarice Chalmers Chair of Engineering Design, and his research lab is the Cognitive Engineering Laboratory, the CEL. Greg's research program addresses theoretical, empirical, and applied issues in human automation interaction. Projects focus on the analysis of cognitive work and the design of representation aids to support human operators in complex systems. Tonight, Greg will speak on automation and human performance, what helps and what hinders, to examine how human factors design principles align human and machine responsibilities, in this particular case, in a nuclear power setting. And a quick note on the session tonight, this research spotlight is being recorded and we will share it with everyone after the talk. And as noted, there will be a Q&A session in the Q&A chat box at the bottom of the screen. Please type your questions into the chat and they will be answered in order. So thank you, Greg, for joining us tonight and looking forward to hearing the presentation.
Thank you, Kendra. It's always a kind introduction when someone doesn't mention exactly how long I've been at MIE. So I do appreciate that omission. I'll start by saying I've been looking at the attendees list. It's a real pleasure to see a number of names there that I recognize, former students and also industry colleagues. It's fantastic to see that you've joined here. So thank you very much for taking the time. Thank you for being part of our MIE community. And hopefully I can tell you a little bit of an interesting story about some things that we've been working on in my research group, and then I'd be very interested to take your questions. So if all works well here, I will share my screen. Very good. And Kendra, can I just get a quick confirmation from you that that's all looking good? All right, very good. Thanks very much. So this presentation today is a culmination of a number of years of work that I've done with some colleagues at the Institute for Energy Technology in Halden, Norway. The paper was published in 2021 in the journal Human Factors. And we were very pleased to be awarded the Jerome Eli Award for the best paper in the journal in 2021. And the paper had a different title in the journal. I was convinced by my communications people that a more accessible title would be preferable for this audience. So today we're going with automation and human performance, what helps and what hinders. So I hope that you're able to enjoy and have some feedback for me at the end. So I'd like to start by acknowledging my colleague on the paper, whose name is Gerd Skroning Jr. from the Institute for Energy Technology in Halden, Norway. Gerd and I have had the pleasure of collaborating for about 15 years now, and he's been a integral contributor to everything that I've done and has created research opportunities for me and for my students that are really I couldn't possibly have hoped for in my career and couldn't find anywhere else in the world. So so please know that everything that you're about to see is as much his work as it is mine. So for those of you who are graduates of our industrial engineering program and took a human factors course in the time that you were at U of T, you'll recall that in the human factors program, we talk a great deal about the process and the consequences of automating work. And in contemporary human factors, there's essentially a lingering concern or a lingering fear about introducing too much automation into technical systems that humans have to remain aware of and engaged with. And so we tell ourselves these stories as a research community that as we increase the amount of automation in highly technical systems, we risk a number of adverse outcomes that we might categorize as a loss of situation awareness, or the risk of it becoming out of the loop and unfamiliar with what the system is doing. We grow concerned about whether or not operators will overtrust or undertrust automation. We grow concerned about whether or not operators understand the automation and how the automation influences the direction of an underlying process. We worry about how complex these processes have become. We recognize sometimes that adding new automation introduces new opportunities for systems to fail in unexpected and unanticipated ways. We grow concerned that people will be biased to accept or reject the inputs from automation agents. We worry about increased cognitive demands, sudden workload transitions, and when that workload is low, we worry about operators being understimulated, becoming disengaged, and losing vigilance. And then finally, over time, we worry that if automation takes over the jobs that humans are doing, that those humans will lose their skills in those jobs. So this is quite a long list of concerns that human factors people have about the introduction of automation. And at times it leads to this sense that we're apprehensive about introducing new control technologies into the workplace. But fortunately, we as human factors engineers have a long tradition of coming up with solutions to these concerns as well. And so we have, over the decades, introduced this notion of providing information about what automation is doing. And many prominent human factors researchers have promoted this idea. So going back at least as far as Sheridan and Verplanck, 1978, who said in monitoring, he was talking about teleoperation systems, the teleoperator and environmental states should be apparent to the operator, especially if he needs to intervene. Oh, sorry. There we go. Slides advancing. Don Norman, who you may recall as the author of The Design of Everyday Things, previously known as The Psychology of Everyday Things, as far back as 1990, said the problem is not automation, it's the lack of feedback. In the 1990s, in the aviation space, Charles Billings said, as automation complexity increases, it becomes more difficult for the designer to provide obvious, unambiguous information about its processes to the monitoring pilot. I call this opacity. You may have heard of Dave Woods, Klaus Christofferson, a graduate of U of T MIE undergrad and master's program, together said, increases in the complexity and autonomy of machine agents requires a proportionate increase in the feedback they provide to their human partners and their activities. More recently in the human factors space, Jesse Chen has said that incorporating transparency should allow an operator to gain understanding of an agent's reasoning process behind its actions and help the operator make informed decisions as to whether he or she should intervene. And then finally, just earlier this year, Chris Wickens, and if any of you recall a name from your undergraduate or graduate human factors training, hopefully this is the name that you recall. Certainly the most preeminent scholar of human factors said that providing greater transparency of automation's working should support human failure intervention by restoring situation awareness. And so we are continuously, over a course of 45 years, promoting this same idea that providing information about automation will allow us to get around that list of concerns that I introduced in the second slide. And currently, the contemporaneous term for this in human factors engineering is automation transparency. But increasingly, we're seeing a proliferation of terms in not just in human factors, but particularly in an explainable artificial intelligence, where we see words like explainability and interpretability and predictability and directability. And so there's a lot of words that are being tossed around. And very often it's difficult to understand if people using these words are talking about the same thing, or are they talking about complementary ideas? If they're talking about complementary ideas, how do these ideas fit together? And it's led to quite a lot of confusion about what these words actually mean. And so we have done some work. One of my graduate students, who I'll mention a couple of times in today's presentation, Fahime Rajabi Yazdi, has done work in doing a scoping review on the different uses of these words and trying to understand what these different words mean. And she's written an article that's in review with IEEE Transactions in Human Machine Systems right now. Another student of mine, Davide Gentile, and my MIE colleague, Birsan Danmez, has been doing work in different types of explanations that we might provide to operators using machine learning systems to try to understand what types of explanations will lead to the best understanding of what those algorithms are doing and what they're saying that operators should do. So this is very much contemporary research in the human factors area and in my lab in particular. And it's a real pleasure for me to work with these outstanding students as well. So where we find ourselves right now and in the work that we're presenting today is behind what we're at least naming the automation transparency principle, which is the notion that making the responsibilities, capabilities, goals, inner workings, activities, and or effects of automation observable and understandable to operators will mitigate the costs of over-automation that we introduced earlier. And so we're going to talk a bit about a series of experiments that were done in Norway with operators from Finnish and Swedish nuclear power plants, and give you a sense of how we study this question, or how we have studied it in the past, and what are some of the results, both expected and surprising, that we've gotten in studying these types of introductions of information about automation to operators and how they react to that. So we have conducted, and when I say we, I mean this Institute of Energy Technology through what's known as the OECD NEA project called the Halden Human Technology Organization Project, which is an international consortium of nuclear nations that are concerned about nuclear safety and collaborate together to explore research issues on that topic, one of which is human performance in the control of these nuclear processes. So in these environments, you can see this is a full scope simulation setting where we have plant models, executable real-time plant models, and operating crews that come in from usually from Sweden and Finland to participate in week-long experiments where they are essentially operating plants that they're quite familiar with the introduction of manipulations in crew composition or information provided to the operators or different designs of control systems or whatever other technology we're interested in studying. And so it's a very high fidelity simulation environment. It's a very tedious place to collect research. There's a lot of time and energy. It effectively takes about 1.5 years to run a single study in this setting. So it's a great, a large number of resources, both in terms of human hours and dollars that are put into making any one of these experiments happen. It takes about 15 to 20 researchers and subject matter experts in order to pull off a single experiment in these settings. So the objective of this research is primarily to inform the development, the regulation, and the operation of nuclear facilities. We seek to offer compelling evidence to these different stakeholders who need to perform their jobs with knowledge that come from representative experiments. And so that's the objective that we have in this research program. So I'm going to tell you about 3 experiments. Actually, the first 2 are largely redundant to each other, and then the third one quite different. And these were conducted over a number of years in this research setting. You can actually see an older generation of the research setting and a newer generation of the research setting reflected here. In the first experiments, 1 and 2, the type of automation that was being employed was what might be called lower level or local automation, which is automation components that act at the component level of the plants. So these might be things like interlocks and controllers or limitations, protections, simple programs that work on a relatively small group of components. And seem to the operators to act relatively locally to the equipment in the plant. In experiment 3, the automation that was used was characteristically quite different. It was a plant-wide procedure automation. So you can imagine essentially an automation that was meant to take an operating procedure and execute the operating procedure. In this case, it was an operating procedure to not quite start up the plant, but run up the plant from a low power setting to a higher power setting. And this automation can execute procedures, takes over this goal-driven task work that operators would normally do. It affects the operation of the whole plant. And it essentially works like an autopilot. You can kind of imagine an autopilot or an advanced driver assistance system in a vehicle that the automation is largely taking over the operation of the facility, and the operators are largely there to monitor that execution and to intervene if any sorts of problems arise. So for experiments 1 or 2, you can see in the upper left the types of information displays that were introduced. So if you look at the top and the bottom, you'll see a lot of common information between those 2 images on the upper left, and then you'll see a lot of added information in the display on the bottom. And so that's the attempt at introducing transparency into the display. So adding into the mimic diagrams that the operators would be familiar with in their daily operation, adding to that information about those interlocks and controllers and simple programs that are executing in the interface. In contrast to that, in experiment 3, where we had that plant-wide procedure automation, you see the contrast in the lower right part of the screen. So it's actually quite typical when you have automation running in these facilities that you have a simple display that basically says the plant is under automatic control. But the industrial designers in Halden created these new, we call them the circle displays, or the donut displays, which were dedicated displays for the operators to show them what it was that the automation was doing. And our expectation, of course, in all of these experiments is that as we provide information, as we provide more information about what automation is doing to the operators of the facility, they will be better informed about what the automation is doing. And so in classic human factors, empirical terms, we mean that they will perform their tasks more effectively or faster, that they will have better situation awareness, that they will not experience peaks or increases in workload. And which one am I forgetting? Oh, that they will have more appropriate trust in the automation as well. And so these are the expectations. And as we went into the experiments and the early experiments, we found exactly what we expected to find. So in experiments 1 or 2, you can see the actual things that were measured: response time, task performance, a human automation cooperation scale, trust in the automation, workload, and situation awareness. And you can see the 2 sets of check marks are experiment 1 on the left and experiment 2 on the right. And you can see in experiment 1, we basically saw everything that we expected to see. The trust in the automation, the situation awareness, perhaps those results were not quite as strong or quite as reliable as we might have liked. And it was actually the case, and this is surprising, if we go back to what I told you about how long it takes to run one of these experiments and how many resources go in. The researchers were actually skeptical that the results were so good. And because they were skeptical, they ran the experiment a second time. And that's unprecedented. That had never been done before in this research setting, where they felt the results were so good that they were skeptical that they could be that good. And so they made minor changes to the display. They actually added some voice sonification of alerts and alarms. And in the second time they ran it, they got even better results. So it was kind of, we were blown away by the effectiveness, the apparent effectiveness of this automation transparency principle in action. However, a number of years later, when we wanted to move on to testing the concept with this plant-wide automation in experiment 3, we were quite shocked by the results. So in contrast to this clearly systematic and strong effects that appear to support the anticipated benefits of automation transparency, in experiment 3, we're observing results kind of pointing in all directions. We had some that were confirming our hypotheses, but some that were directly disconfirming, and some that were actually inherently contradictory to themselves. There were a lot of confusing interactions. It was actually a very difficult set of results to interpret statistically, but clearly lacking that systematic set of benefits that we observed in experiments 1 or 2. And in particular, we were concerned about one result, which was that when challenged to detect deviating process states, which is a serious concern in the nuclear setting, the results actually showed that that task performance was negatively affected by transparency. And so this is a substantial safety concern. This is exactly the type of result that we don't want to see in this type of experimentation, and the type of result that we want to share with technology developers and regulators and operators of this type of technology. And so it's quite a serious concern. I'll show you another representation of the results. It's a much more complex representation of the results. This is what we hope is a useful and innovative way of presenting results from experimental research. For those of you who don't want to get too far into the details, you can sort of see on the left 2 panels, so the left panel and the center panel, we have all of the variables in the study, all of the outcome variables normalized such that a line going from lower to higher means an improvement. And so you can see measure after measure after measure from experiment 1 and experiment 2, all of the results are going in the right direction, up and to the right, again and again. And that final column is how we interpret the combination of effect size and statistical significance to develop a comprehensive understanding of what these data tell us. And so what we see in this representation again and again is these long blue bars that say, yes, here is a clearly systematic and large effect on the performance that is exactly in the direction that we expect to see. When you look at that third column, you see a couple of blue lines, blue bars, but you also see a number of red bars. And so these are trending in the exact opposite direction. And you see rows that have both blue bars and red bars, which are pointing to that contradictory information that in some conditions we saw improvements, and in other conditions we saw decrements in performance. And so hopefully this is a salient way of us sharing with you a lot of research results from these studies without going into to showing you dozens of graphs and interpreting a lot of p-values and that sort of thing, which some of us really enjoy, but most of us would rather leave for the thesis defenses that we don't have to participate in. But so this set of results actually really left the researchers at the Institute with really conflicting feelings about this transparency principle and an uncertainty about where to go. And in fact, we have, through a number of technical reports, posited a lot of different potential explanations for why the results might look the way that they look, and whether or not it had something to do with the interface design or the way the crews were comprised in the different studies, whether or not these results were really methodological phenomenon, or if it's the different instruments that we use that worked in one setting and not another. And so we've actually spent years trying to interpret these data. But our overwhelming sense was a sense that our ice cream had fallen off the cone, and this clearly what we thought beneficial principle, this principle that we've been talking about in human factors for the better part of 45 years, that we've been teaching our students to adopt and to apply in their work, whether they're doing research or whether they've gone off into industry to work. The general idea that providing operators of a high-tech system with more information about what the operator was doing is going to benefit the human performance. And then, well, it didn't. And why? What's happening? What's different in this later setting than in the earlier settings, especially when the newer setting, the most recent experiment 3 result, that type of automation seems more similar to the types of automation that we're increasingly seeing in not just complex industrial systems, but increasingly in commercial consumer systems as well. And so the best explanation that we've come up with so far, the explanation that is really driving our ongoing research questions, is that when automation acts at the component level, it acts sort of as a local tool embedded in a technical system that the operators are familiar with. And in that case, transparency as a principle doesn't have a lot of impact on the control of the plant. And it's having a lot of small impacts locally, but that those may be easier for the operators to use. And we can sort of think about, like, electronic stability control, which if you have a vehicle that was built after, I don't know, probably like 2005 or something like that, your car probably has electronic stability control or some version of it, such that when you're trying to drive in a particular stop on a slippery surface, that system is adjusting the amount of braking power that's applied to each of the wheels of the car in order to maintain traction and maintain control of the vehicle. And the driver is never aware of that for the most part. I mean, the light may go on your dashboard, but it doesn't change the way that you drive the vehicle. Anyone who's young and has not driven a vehicle that is older than that, watch a movie from like the 1970s, 1980s that has a car chase in it, and watch the way that the vehicles perform dynamically as they corner in particular. And you'll see the effect of electronic stability control just in contrast of those vehicles to cars today. And so you can imagine this is an extremely valuable safety intervention that engineers have created, and it saves thousands and thousands of lives every year. In contrast, in experiment 3, we have an automation that is taking over control of the whole plant and is closely coupled with and even changing the task work that the operators are performing. And it actually changes what we call the operational concept. In the nuclear domain, we talk about the concept of automation. What is the concept of operations? What is the idea that we have for how the different agents involved are in control of the process? And when those things change in unintended ways, then operators can be taken by surprise. And I think we see this also in advanced driver assistance systems in vehicles, in very modern cars, particularly higher end vehicles. Now we're seeing these driving assistance systems that do more than just adjust the power to brakes to stop us from sliding in snow and ice. And now they're taking over planning of the direction of where the vehicle is going to go. It's doing lane centering. It's aware of traffic as you use cruise control. It may allow automatic lane changing or self-parking and even semi-autonomous navigation. So these things are very significantly changing the concept of automation of a vehicle. And we see this evolution in control technology happening across domains. So perhaps I could have introduced here a paper that Geert Skroning and I recently did on the 737 MAX accidents. And of course, there are many perspectives on those accidents, but one of the perspectives that we can take is questioning the transparency, the idea, what ideas did the Boeing engineers have in mind when they introduced a control system into an aircraft that changed the way that effectively changed the operational concept for the platform under certain conditions. And pilots clearly did not understand what it was doing, and resulting in the two major loss of airframe accidents. So we think quite a serious long-term issue. So who else is working on this question? Well, fortunately, as automation transparency has become such a widely used concept, there have been a couple of reviews of automation transparency, one by Bhaskara and her colleagues in 2020. Her primary conclusion is that there's emerging evidence to suggest that transparency can increase the accurate use of autonomous agents by human operators. However, evidence regarding which precise level of transparency, so she's basically saying how much information you provide about automation, which level would yield the most accurate use of agents, has been far from consistent. So she recognizes that sometimes having transparency is beneficial, sometimes having transparency is not as beneficial, or even potentially a detriment. Koen van der Merwe in 2022 said there's an overall trend in the data pointing towards a beneficial effect of transparency. However, the data reveals variations in situation awareness, mental workload, and operator performance for specific tasks, agent types, and level of integration of transparency information in primary task displays. So you see the sort of generally positive tone with reservations. Not everybody has been so reserved, though. Chris Wickens in 2022, in the most recent edition of the Engineering Psychology and Human Performance textbook, that if you took the fourth year course that Professor Paul Milgram has primarily taught over the past years, you would have used this textbook. This is the latest version of this textbook. And Wickens and his colleagues say that that the results of 15 recent studies offer unqualified support for a transparency benefit to performance. So there's a much stronger statement. And in 2019, Wickens actually referred to automation transparency as providing a free lunch, which we interpret to mean a benefit to task performance or situation awareness or appropriate trust, without a cost in terms of workload or some other performance outcome. So an exceptionally strong positive endorsement of the automation transparency principle that is one that causes us a little bit of concern. And in particular, some recent work that one of my students, I mentioned Fahime Rajabi Yazdi earlier. Fahime has been doing a statistical meta-analysis of automation transparency. And I'm going to show you sort of two sets of results. The first set of results is the way that you're not supposed to do this. And so please take this with a substantial grain of salt, because there's a lot of arguments for why we shouldn't look at data this way in a meta-analysis. But it is still telling that if you look at the four sort of primary categories of dependent variables: task performance, trust and automation, workload, and situation awareness, you see across the dozens of studies that Fahime has looked at, many comparisons between either no transparency and some transparency, or small amounts of transparency and larger amounts of transparency, that the number of those comparisons that point in to a direction, in the direction of showing a benefit, is always less than 40%, right? So it's very difficult for us to reconcile, looking at these numbers, how Wickens and colleagues found 15 studies that showed unqualified support for task performance, right? So unqualified presuming to mean that there's no cost to trust, workload, or situation awareness. More recently, Fahime's very recent work, this is now only looking at task performance data. So statistical meta-analysis is an extremely meticulous type of research to do. And Fahime, to her great credit, has been laboring through this for months and months and months. And entering these studies into to software that's meant to do meta-analysis. And what you can see here, these are not selected studies based on results. These are studies that we have the data readily available to enter into a meta-analysis. And essentially what you're looking at here is a confidence interval. And if you recall your statistics, when your confidence interval crosses over the value of 0, you essentially don't have you cannot draw a confident conclusion that your intervention is having an effect. And so you look here that interventions to the left favor the control, the non-transparent intervention, and the results to the right favor transparency. So those transparency interventions providing more information. And so our meta-analysis is telling us that and we obviously need to repeat this for workload, for situation awareness, for trust and automation. But when it comes to task performance, it's really difficult to conclude that we have an intervention here that we can reliably say will benefit human task performance in these settings. So, sorry, there's a little bit of animation here from Fahima's slide that I'm not familiar with. But it brings us to our conclusion that at times in human factors, we need to be careful when someone offers us a free lunch. And we have a lot of work to do here still in this research area, but we hope that in the near future, with the complete meta-analysis, we'll be able to encourage human factors as a science to be a bit more skeptical about this principle that we've been effectively touting for close to half a century. So with that, I will finish and hope that I have encouraged you in a way that you'll have some questions for me to answer. So thank you very much for being part of today's show.
And thank you for Professor Jamieson for joining us and for the free lunch slide, because that will always motivate me to do most anything, regardless of the positive or negative outcomes. So thank you everyone for attending. It's been lovely to have everyone here. This is the Q&A portion of the research spotlight. So please do, in the Q&A chat box at the bottom, please do type your questions in. We have one from Will, making a geographical correction, something about Russia and not Turkey. There was something about Russia.
Oh, I had mentioned how far Norway extends as it goes to the east, and yes, I mean it goes. Oh. It goes over Russia geographically, but the question is how far over does it go? And it goes over as far as Turkey. So yes,
we're not even related to the talk.
Oh, but yeah, it's important. It's very important that we get these things correct. It's useful to have a sense of how wide Norway is, because it actually looks like a really skinny country.
And then we have one from Rick Ross asking, are there different types of transparency that may result in different results?
You know, I think this is one of the questions that we need to be asking. And it's one of the things that makes Fahime's work very, very difficult, because right now we're introducing the concept as if it's generic, as if we can apply this idea of more information about automation in almost any setting. And that's the way that the reviews of transparency have so far looked at things. But Fahime will tell you that there are many different actual types of intervention, different types of information about automation that is being presented in these different studies. And it's quite possible that some of these interventions are effective and others are not. And so it's actually a challenging working back through those studies to figure out, well, how can I compare one person's intervention to another person's intervention? And so it's possible that we might be able to code studies or categorize studies in a way that we can discover that there are certain types of interventions that are consistently beneficial and other types of interventions that are less reliable, less consistently beneficial.
And we have a couple of participants who have raised their hand. And so Peter has just put his question in here, so we could allow you to speak, but I will read out the question and then we can open it up a bit more. So Peter is saying automation can cause other outcomes that need to be considered in advance. 1, people may lose their jobs, political problems, question mark. 2, customer-facing kind of automation could lead to reduced customer service and lack of human touch. And 3, could be a safety concern. Would like to fly in a plane without any pilot. So comments on that.
Absolutely. So I'll start with the last one. And actually, I think this is a good question to connect to the last question, which was about different types of automation. Now we're thinking about different types of outcomes, right? And so in this research setting, we're primarily concerned about the connection between human performance and safety, right? So we're talking obviously about a safety critical system. For those of us who are here living in Ontario, we want to know that our nuclear regulator, the CNSC, is holding Pickering and Darlington to very high standards of human performance, because we know that that connects to safety and helps us to avoid situations like Chernobyl and 3 Mile Island and Fukushima. So absolutely, we're looking at that. But then these questions about, for example, employment and ethics. There's also some extremely interesting work about the effects of culture and the effects of automation on culture, right? So we have a tendency to design automation in the Western world from this Western culture that we have. We have an idea about how different agents in an organization should work together in terms of authority structures, in terms of what the characteristics of the automation should be, right? Like, can we put an automation that adopts a female persona into a culture that has a male-dominated hierarchy, like authority hierarchy? Like, what would be the implications of that? So there are a lot of questions like this, and while I don't have I don't have my own research to show you on that. What I can tell you is I teach a course. It's MIE 1412, Human Automation Interaction. I've seen a number of students from the course there, and those students can tell you that we do read papers about culture, and we do read papers about economics, and we do try to consider a wider breadth of impacts of automation on us rather than just on our task performance. So thank you for that question, and I can assure you that is something that is in the conversation right now.
Wonderful. We have a question from Leo asking, what are your thoughts around your current studies on automation and SMRs, and how multiple SMRs will be managed from a remote control room?
Wow, Leo, I wish you were here to talk to me. I don't think I know Leo. Please reach out to me. Right now, one of the things that I'm working on, the NSERC, the Natural Science and Engineering Research Council of Canada, and the Canadian Nuclear Safety Commission together have put forward an academic research funding opportunity that I'll be writing an application for on small modular reactors. And so for those of you who don't know, a small modular reactor, the two words are, so it's a nuclear plant or facility that is small in the sense that it's smaller than most large-scale power reactors, are 600 to 1,000 megawatts electric. Small modular reactor can be anywhere from about 30 to 300 megawatts electric. There are also micro reactors that are like 5 to 10 megawatts electric. And these reactors are also modular in the sense that they're more replaceable. So you can imagine that it would be much easier. These reactors are typically designed to fit on a rail car, could be transported from a manufacturing facility to a production location, put into operation at that location. And then when the fuel is exhausted, that you could remove the whole reactor, send it back to a facility that could safely remove and secure the fuel from the reactor. So small, modular, huge benefits to the economics of nuclear power, and also potentially huge benefits to getting power sources to remote locations, which I think leads to Leo's question, because then the reactor is potentially far away from an urban center. Do you have the local expertise to operate that thing? Could you have, particularly when you talk about micro reactors, could you have more than one in a location? And then would you have a small group of operators operating multiple plants at the same time, which is very rare in the nuclear context? Or would you potentially even have a single operator monitoring a nuclear reactor, which is also extremely rare in this context? So the research that we're going to put forward, don't anybody tell my competitors to this, is this question. So I call it the N by M question: N operators and M reactors. What are the implications of N operators operating M reactors? There's very, very little research on this question of how many systems can be controlled by a small number of operators. We have seen it in the unmanned vehicle context, but there's just not a lot of this sort of capacity research out there. And then the other question is, what if you're remote? And you're at a distance, at a remove from the reactor? How would you do that? Would you do that through virtual reality? Would you do that through some other means of being aware of what's taking place in the facility? So these are fantastically interesting challenges. Hopefully we'll be successful in getting the award, and we'll have a chance to investigate some of these things. So if you're interested in that sort of thing, please reach out to me, because right now I'm trying to understand what the industry, public interests and concerns are about small modular reactors, so that I can factor that into my proposal. So thanks for your question, Leo.
We have a question from Shane. Shane, it's been a while. Thanks for joining tonight.
Hello, Shane.
His question is, if you are starting to see data that sheds skepticism on transparency's free lunch, why do you think the human factors community has been so enamored with it and unquestioning for decades?
So for those of you who don't know Shane is a provocateur, and I love that about Shane, because I am at times a provocateur myself. So thank you for the provocative question, Shane. It's good to hear from you. So I hesitate to give this answer because I don't even know if I want to explain why I'm hesitant. I believe that there's a lot of received wisdom in human factors, and we have a tendency to want to generalize relatively simple and thin results. And I think we do that largely because we want to have an impact. We want to have an influence on how technology is designed and adopted and critiqued. But I think often we do that with an insufficient evidence base. And so I embrace that skepticism. I like that skepticism, but I'm an academic. I can get away with being skeptical. Developers of nuclear technologies and other types of advanced technologies, they can't get away with it. They have to act now. And they have to act on insufficient evidence about how these technologies are going to impact human performance. And I think that there's a real pressure on human factors engineers to answer the questions that those technology developers and those regulators and those operators have. And so I think we have a tendency to overinterpret the evidence that we have because we want to be able to answer the question. So I think that one of the things that I should say more in my own vocabulary is I don't know. And I think that that's something that human factors, the human factors research community should be saying more often. We just don't know the answers to some of these questions.
Thank you. We have a question from a Mr. Paul Milgram asking, or should I say Professor Emeritus, Professor Paul Milgram, is it possible that there might be a potential age effect at play whereby younger operators might interact differently with automation, including transparency, especially with regards to trust, etc.?
Absolutely. This is something that gets discussed a lot in the nuclear sector because for a long time, nuclear has not been a sector that's attracted young engineers, unfortunately. And there have been efforts in place to try to change that. The SMR evolution of the nuclear technology, I think, is going to really change who we get into this space, both as engineers and operators. So yeah, now has there been, to my knowledge, I don't know that there's been any research in the nuclear setting to test that question, whether or not, or even how to frame the question. I'm not even sure how I would frame it. But there certainly is discussion. How are operators that might be getting trained now, how will they have different competencies? Will they have different expectations? Will they have a different comfort level with automation? I imagine the answer to all of those things is yes, and that we need to learn more about how that's changing.
Wonderful. We now have a question from Rob. Let me just pull it up here. So his question starts off, our original approach to display design was to reduce the amount of information given to the operators, speaking of the design of Darlington NGS back in the 1980s. The more transparent display seems very cluttered and busy and could be confusing. Perhaps that is why the automation was not as accepted by the operators. We also looked at providing the operators with decision-making assistance by analyzing raw data and providing alternates as to what the problem was and the potential resolutions for it. Comments?
Wow, a lot. There's a lot there to comment on. One thing that I think the complexity of a display, or I'll say the perceived complexity of a display, depends heavily on the experience of the person that is using it. So you could, if you see sort of young people playing some video games these days, the complexity of the display, in my eyes, is extraordinarily high, and yet they might be able to cope with that information very effectively. So yes, I've had the experience of introducing displays to operators and having them say, it's cluttered, it's too complex, that's going to make my job harder. And so certainly there is a concern about whether giving, like, is there an incremental value or is there a diminishing return of new information that's provided? And that, yes, that could very much be the case. I'm sorry, there was more to the question that I've not responded to. I don't know if Kendra, if you feel like you can in real time sort of pull out another piece of it.
So there was the cluttered design. Oh, and it said, we also looked at providing operators with decision-making assistance by analyzing raw data and providing alternatives as to what the problem was and potential resolutions to it.
Yeah, and this is where I think that there's real opportunity here, because effectively what we're asking operators to do is to make decisions, right? Increasingly so. And so aids that support that decision making can be very effective. They also can be potentially deceiving, right? So one of the things we have to be really careful about when we offer a decision aid is, does the aid know when it is at risk of providing bad advice, bad input? And so that's a real challenge to define the operating regime in which the aid is meant to be helpful, and that outside of that range, it is not, it doesn't really have the capability of being helpful. So how can we communicate those limitations to operators becomes an important question. The last thing that I'll add, and this goes back, people who have taken a course from me will know that I always get back to Lizanne Bainbridge and what she refers as to the ironies of automation. And one of the ironies that she raises is that engineers have a tendency to automate the things that are most easily automated. And unfortunately, the things that are most easily automated are often the things that operators don't have difficulty with. So I'm doing some research with Professor Farzad Halfati, who is interested in medical imaging and machine learning in medical imaging. So if you have a machine agent that's reading a medical image and saying, I think that there's a certain type of lesion in this image. Well, those systems are quite good at catching the lesions that radiologists don't have a lot of difficulty detecting, but they're not so good at the really complex cases, which are already difficult for the radiologists. So, how much value is there in having a decision aid that aids in a decision that's easy to make versus and doesn't particularly help with the things that are difficult to do? So, this is where we get into wanting to, as human factors engineers, wanting to get involved in the technology design process and try to encourage the automation designers to think about what's hard about this job, what's difficult about it that we can support with technology, instead of asking, well, what can we do with the technology that we have, and then tell yourselves you're helping the people who are doing the job because you've potentially made a not too difficult decision easier to make. Yeah, great set of questions built in there.
Wonderful. We have another question. We have a question from Andy. Andy starts off by saying, I am not familiar with the subject matter. What does workload mean in the context of automation? I thought automation meant less/no workload.
Okay, so this is actually a more difficult question than Andy might think. So workload typically we use to refer to the amount of effort that needs to be exerted by a person to perform a task. And we might imagine in typical measures of workload, divide that into different categories. And so sustained attention might be considered one type of workload. Physically lifting something up and putting it down would be considered a different type of workload. So we may describe workload according to different dimensions. And certainly when we look historically at automation, the way automation has evolved over the last century or so, it was initially brought in to replace work that was very obviously physically effortful. And that work, when replaced by a machine, we could pretty readily say that had reduced the workload. What becomes challenging actually is that operators, humans, we actually seem to need a certain amount of stimulation in order to be effective. And so if we take away too much of the workload, if we take away too much of what's challenging about work, we actually make it harder in different ways that we don't anticipate. That it can just be flat out difficult to remain engaged and remain interested. So I was talking to a company that develops microreactors today, and they said, our human factors concern is that the operators will have nothing to do for such a long period of time that when we actually need to do something, like what will they, what state will they be in when that time comes around? And so very low workload is actually a concern. So we're qualitatively speaking, looking for a range in which we've removed certain types of workload and certain amounts of workload while retaining enough to make the job interesting and challenging enough to remain engaged in. And that's a really difficult tuning process to do. So Andy, I hope that's been a helpful introduction to the concept of workload.
We have a couple of more questions. We have one from Gail Ross, hi Gail from BARC, who we've done some capstone
Oh,
projects with.
hello, Gail. What a
Um,
pleasure to hear your name.
Wanted to say hi and thank you for enjoying the presentation. She does ask a question on, have you done any work on the air traffic control systems?
Myself, no, but Jörg Skroning, my partner and research partner, has done work in air traffic control with Eurocontrol in Europe, and there are other researchers who have done a great deal of work on that subject as well. I will share. Gail and I did projects together a number of years ago on safely restraining dogs in vehicles, and we had a great deal of fun with that. So Gail, it's a real pleasure to hear your name again, and I hope that you're well.
I remember the capstone projects
Do
from
you?
I worked on them in 2016. So it looked like
Nice.
a really great project to be part
Oh,
of.
it was an absolute blast. So look up Gail's BARC organization. It's fantastic. So good to have you here again.
We have a question from Tabish, and it is, I can see too much transparency overwhelming operators due to the amount of information being displayed. From a human factors perspective, why not put comprehensive displays as a secondary screen and put requires attention or key current status information front and center?
And that is that is effectively what a lot of designers are working on now. But those donuts that I was showing you, those donuts were designed by very skilled industrial designers, right? So these are people who know the domain, who know the work, who have enough knowledge of the technology, working in concert with subject matter experts, psychologists, and plant experienced operators. And they thought that they were getting the right amount of try and use your term, comprehensive information versus overview information. They thought they were getting the right amount there. And evidently they were at least partially wrong. So it has proven difficult. Certainly one of the things that we try to do is to communicate a sense of urgency or novelty, might be another word for it, excuse me. Trying to work to direct the operator's attention to the information that is most valuable at a given point in time. So that really falls under the category of what we now call adaptive automation. And so we can adapt potentially, one of the ways that we can develop adaptive automation is to adapt the amount of information that we provide at different times. And so to go back to that workload concept, if we knew that the operators were in a low workload period, we might actually hold information back from them. We might try to make them work a little bit harder in order to keep them engaged and keep them active. Whereas if alarms started to sound and the facility started to get into a realm of caution or concern, we might actually start to filter the amount of information we provide about the automation or about the plant in order to help regulate that workload. So that's being increasingly done in an adaptive way, not deciding in advance all the time how much information an operator will need, but trying to adjust it. And of course, you can imagine it's a very delicate adjustment to make.
Excellent, thank you. We have one follow-up question from Andy, and this will be our final question of the evening. So Andy's follow-up question to the workload question is, do people's preconception mental model of what the procedure is affect the outcome of the experimental results?
Absolutely.
People who have never driven a car may not be as surprised by procedural automation of self-driving than an experienced driver. An inexperienced nuclear power plant operator may embrace automation with less transparency, more so than a seasoned operator.
Yeah, so in human factors, this is close to the concept of negative transfer of training. So the idea that your knowledge and experience that you've acquired, through training or even through operating experience, can actually be a detriment if the system changes in a way, if the technology changes in a way that is not consistent with your knowledge and training, it can actually, your knowledge and experience can actually work against you. So yes, generally, like often, and this goes back to some people in the audience might remember Professor Kim Vicente, who used to get quite agitated when someone would say, well, design the technology to be consistent with the person's mental model. And Kim would sort of, jump up and down and say, but what if the mental model is wrong? Like, why would you want to design for a misunderstanding of the technology, of the underlying technology? And so, yes, if the mental model is correct, it makes sense to try to design to that. But mental models are very often wrong. I mean, you can go. I mean, there've been studies. If you tie a weight to a string and a pencil, and you swing it around and you cut the string, what is the trajectory of the weight that that the weight will follow? What trajectory will the weight follow after you cut the string? Physics students get this wrong, right? So we all have mental models of even simple systems that are mistaken. When we get into these very complex systems, the mental models can easily be wrong. So yeah, good question.
Wonderful. Well, again, thank you everyone for joining us tonight. The recording will be shared with everyone after the fact. And again, a huge thank you to Professor Greg Jamieson for speaking tonight, and looking forward to hearing research updates from the next round that's coming out. So thank you again, Professor Jamieson. It was a pleasure to have you on tonight.
And thank you everyone for joining and being part of the MIE community.